Hi, this is Amanda Birch.
And this is Daniel Wieland, and today we'll be talking about emission intensity. Emission intensity is what is displayed on the y-axis of an emission spectrum. It is proportional to the number of photons that are released at a certain wavelength. This is what produces the emission spectroscopy curve. Thus, the lambda max emission point is the wavelength at which the greatest intensity is observed.
To model the effect of each of these factors on emission intensity, consider a piano. When a set of keys is pressed, the output is a sound at a given volume. The loudness of each note represents the intensity of that wavelength, and the loudest note is the lambda max. When the same set of keys is pressed much harder, representing a greater input of energy into the system, the intensity or loudness of the sound is also much greater. However, this trend cannot continue forever. At some point, the intensity caps out because the instrument simply cannot release any more noise per second. This is also true for substances undergoing emission spectroscopy. Because intensity is proportional to the number of atoms in the excited state within the sample, the number of atoms of the substance present limits the intensity to a certain maximal level. The intensity can be increased above this apparent cap if there's a higher concentration of the substance, in the same way that a large piano can play louder than a small piano. One other factor that affects intensity is molecular composition and intermolecular forces. Different molecules under the same energy input emit light at different rates and different wavelengths. This is dependent on how relatively unfavorable each excited state is compared to the ground state, which is influenced by molecular composition in IMFs. This effect can be modeled on the piano as well. The intensity and wavelength of the sound produced by each key is controlled by a hammer striking strings of various lengths and thicknesses. When the same energy is input for two different substances, represented by two different chords, the intensities are different because of the composition of the piano at those points. Likewise, in molecules, the intensity is affected by how relatively favorable the ground state and excited states are. If the ground state is very favorable over the excited state, photons will be emitted more rapidly from the excited state returning to the ground state, resulting in a higher intensity at those photons' wavelengths. Molecular composition of fluorescing substances determines the intermolecular forces that are present between molecules of the substances. This can increase the range of intensities that are produced over certain wavelengths, as the IMFs cause distortions and changes to the relative energy levels that photoexcited electrons can reach.
Of course, this is assuming that the different substances involved do not interact with each other. In some cases, one substance present will absorb photons of a wavelength that another substance present emits. In this case, although the concentration of both dyes is lower in the mixed state, the red dye present actually has a higher intensity than the unmixed state because it is absorbing photons emitted by the green dye. One factor that does not affect intensity is the volume of a solution at a fixed concentration. Because intensity is a measure of energy output per unit time per unit area, having an increased volume of the same substance would not affect the intensity produced. Likewise, an orchestra of 40 people with one piano has the same ratio of pianos to other instruments as an orchestra of 80 people with two pianos. Even though the second orchestra is louder overall, the intensity per piano or per unit area is the same. And that's how energy input, concentration, molecular composition, and IMFs affect emission intensity. Thanks for watching!